this video, we'll walk you through the single factor ANOVA examples using Excel. So for single factor ANOVA, what we're doing is comparing whether or not there is a difference among different classes or treatments of data. So this first example I have here is using my Injury 9 database. I'm looking at the number of injuries sustained in car crashes based on the different class of car involved. So there's 9 different classes of cars involved. They range from 2-door small cars to then small 4-door cars all the way up to like trucks, minivans, all those kinds of things. So there's 9 different groupings here. Notice that the number of observations of industries within each class is not equal. It doesn't need to be. All I want to do is test, is there a difference in the average number of industries across classes? So HO, the average number of injuries is going to be equal across all 9 classes. HA, they're not going to be equal. And the way I'm going to do that is go into data and then data analysis. I'm going to select here ANOVA single factor, click OK, highlight all of my data. I do have labels in my first row, and I want to put my output here so I can find it, and click OK. All right. Now I will look to this between groups that tests HO, the number of injuries is equal across all 9 classes, and my p-value is definitely less than 0.05. So I am going to, okay, I want to make that go away. Sorry about that. I am going to reject HO and say there is a difference in the number of injuries across the 9 classes. And then I can go in here and look and analyze, okay, well, which one has the most number of injuries, most number of injuries, I seem to see in class 1, and I can go through and analyze that data a little bit more. The second example that we're going to do is using the data set Comp Sales 9. Now, this example is going to go into a little bit more depth here. What we're doing is comparing the sales figures, number of, dollar amount of sales, so based on 3 different sales approaches, A, B, and C. So we have these 3 different sales approaches, and we have 15 different sales people, and 5 of them were assigned to each sales approach, and then we looked at their dollar amount of, stop showing me that message. We looked at their dollar amount of sales, and these dollar amounts are in thousands. So I'm going to go ahead and run my same basic single factor ANOVA to test, is there a difference with, between the classes. So, approach testing HO, there is no difference between the 3 approaches. So I'm going to go ahead and do that over here. So single factor ANOVA, here's my data, select off, I have labels in my first row, and I want to put my output over here. All right. And here I'm going to look at that p-value. It's less than 0.05, so I'll reject HO, and I'll say that there is a difference in the 3 sales approaches. Looking at the averages, I can see that approach 3 looks like it's best, but I can go a little bit further than that. And now I actually want to see, okay, I'm just generally saying that there is no difference amongst, or that there is a difference amongst the 3, and it looks like approach C is better. But is approach C necessarily better than approach A? Or is approach B better than approach A? Is approach A better than C? Those kinds of things. So I have 2 methodologies that I'm going to use to test this, the Bonferroni method and the Turkey method. So using the Bonferroni method, I first have to start out by identifying what is my G. My G is the number of different classifications or groupings. So I just remember G for groups And there's 3 different groups because there's 3 different sales approaches. Then alpha divided by 2G, okay, so alpha is always 0.05 divided by the quantity 2 times, I could have just typed in my 3, but I'm lazy, and that gives me a G value. And then B is the T value for alpha over 2 times the number of comparisons, where G is going to be my number of comparisons. Okay, so B is going to be found using the T inverse. This probability, comma, and I'm going to go over here for the number of comparisons. So T value for alpha over 2 times the number of comparisons. So that's the T value for that 0.833%. So that's going to be that probability. And then my degrees of freedom is going to be my degrees of freedom within groups. That's going to be that 12 there. So I'm going to come up with a B value here of 3.15. And again, I just got this information directly off the PowerPoint slides and copied and pasted it over here so I can look at this information. So I'm also going to need SE. That's going to be important. And SE is going to be the square root of the MSE within groups. Okay, so square root of MS within groups. So the square root of 22.7 is what I'm going to look for. So 4.76, that's going to be the SE I'm going to use right here. And then I'm going to just compare each sales method minus the other. So first I'm going to do A minus B, then B minus C, then A minus C. And my upper bound's going to be found using, this plus, and the lower bound's going to be found using minus. All right, so for this upper bound, A minus C, so the average of A minus, you know what, it might help if I, oops, hold on. Okay, this is equal to the average of A minus the average of C plus B times SE. Okay, let's put this in parentheses. Okay, all of that times, now the square root of 1 over 5 observations here in A plus 1 over 5 observations here in C, and I want all of this to be in parentheses to show that all of, this entire second term is going to be added onto there. And I get negative 2.9 as my answer. And then I'm going to repeat the same process. So I'm just going to be lazy and Control C to copy these numbers. Control V, paste them in there down there. But for my lower bound now, it's going to be negative. Okay, so this is comparing approach A and approach B. Now I'm going to go here and do approach B minus approach C. So this is showing, if I look here at the average, when I did this, I did approach A minus approach C. So I'm just going to go and change that label in there, and I'll change this one to B when I'm doing that. Sorry about that. I just noticed the way I clicked it on there. Now I'm going to go in and do B minus C. Okay, so the average of B minus the average of C. Okay, plus B times my standard error times the square root of 1 over 5 for approach B plus 1 over 5 for approach C. Okay, and I actually typed a 5 in there accidentally. Okay, and then I want to put, let's see what's going on there. I want to put all of this in parentheses here, which it looks like it did default for me. That's quite convenient. And then I'm going to recopy this again and just paste it in here and change this plus to a minus. Okay, and then I'll compare A and B using the same methodology. So average of A minus the average of B plus B times SE times the square root of 1 over, there's 5 observations in A, plus there's 5 observations in B. Okay, and again, copy this and just change this plus to a minus now to get the lower. All right, so how do I tell if there's a difference between the groups and whether or not it's statistically significant? So if you have 0 within your upper and lower bounds, there is no statistical significant difference between the two groups. So here, B minus C, 0 is within that range. So there is no difference between sales approach B and sales approach C. Here, in approach A minus B, again, 0 is within that range. There is no difference between sales approach A and sales approach B. But here, A minus C, there actually is a difference because 0 is not within that range. Now the question is, why are these negative numbers? Well, they're negative numbers because I'm doing sales in A minus sales in C. And if I look here, my average sales using C are actually higher. So if I had switched around these calculations and done C minus A, I would have gotten the same numbers, but they would be positive. So what this is actually telling me is that using approach C, I will sell, now my numbers are in thousands here, so I would sell between 2.9 thousand and 21.9 thousand more using approach C than I would using approach A. I can follow the same basic process here using this turkey methodology. And here I'm going to need my same standard error that I had before, but now I have this Q statistic that I'm using there. This estimates, or these three estimates are said to be family-wise, confidence of 95%. Okay, so the estimates can be viewed simultaneously rather than one at a time, and in order to have this 95% confidence. But again, we're basically just doing this for comparison purposes. Is A versus B versus C going to be the better methodology? This Q is the studentized range. It can be found in table 9B in the back of your textbook. I'll also provide a link to an online version, and you'll have a copy of it printed out for you. P, so you're going to look up Q, given information about P and V. P is the number of means being compared, in this case 3, because there's 3 different approaches. And then V is N minus K, where K is the number of comparisons, I believe. Yeah, or K is the degrees of freedom, so K is going to be that 12. So it's really similar to the B that we had used in this calculation here. And that's how I came up with 3.77 that I use in the table. So if we just compare these two equations, they're strikingly similar. You're going to have strikingly similar results. It's just different authors publish different papers around the same time, and supposedly the turkey method is an improvement on the Bonferroni method. I don't know. They almost always agree, but I'll show you how to calculate this one as well. Okay, so we want to start off with A minus B. Okay, so the average in A minus the average in B, and I'll do them in order this time, sorry, plus this 3.77 times, we need this standard error divided by the square root of the number of observations, which is going to be 5, because both A and B, I believe, have 5. Let's make sure. Yes, if they are not equal, you would then, if the sample sizes in each group were not equal, I wouldn't just take this 5 like I am here. Instead, what I would do, I would divide by the square root of 2, because I'd be comparing 2 different approaches, and then multiply that by the square root of 1 over the number of observations in each grouping, like you see here in the Bonferroni method. So this methodology can also accommodate if you have different number of observations in each group, even though it doesn't look like it just based on the shortened formula that I've shown you right here. Okay, and I'll copy that over and change my plus to a minus here for my lower bound. And again, I'm going to follow that same basic logic. If there's a 0 in here, there is no statistically significant difference. So I'm not finding a statistically significant difference between sales approach A and sales approach B. Going over here, I can look at average in B minus average in C plus this 3.77 times this standard error divided by square root of 5. And again, they're equal, so it doesn't really matter which square root I do. Okay, you don't like, oh, there we go. All right, so I'll copy this over and change my plus to a minus. Here again, no difference between B and C, and your numbers are, kind of close, a little different. It's, as long as you're getting confirmation of those same findings, you are fine. Okay, and then I want to do A minus C, so average in A minus average in C, plus this times your standard error divided by the square root of 5 here. Okay, and copy this. Change my plus to a minus. And 0 again is not within this range this time, comparing A and C. So that tells me there is a statistically significant difference in A versus C. Again, same as I found here over here in purple. And again, since I did A minus C and I have negative numbers, this is telling me that C is in fact better than A.